Now this is both the water demand and the supply information that we have put together. And now we talked about the biophysical aspect of it, the biophysical information. Now this is our institutional information. Once water comes to the fields, then there has to be a set of rules that govern how water is allocated. And for this particular system, there are 6 sectors. All sectors receive equal volumes of water. When water is, one of the rules is when water is plentiful, it's distributed on a continuous flow system, meaning all the gates are open and anybody can take as much water as they want at any point in time. When there is scarcity of water, what happens is all the gates are closed, water is diverted to one sector, and then to the next, and then to the next. It's a sequential type of distribution system. And the system also recognizes 2 other types of scarcity. That is, when water is even more scarce, then water is distributed to each sector on a 12-hour basis, and there's more scarcity on a 24-hour basis. Now, to model this, to make this model, the basic equation that we use is it's a differential equation where we relate the standing water height with the combination of check gates and amount of water used, and then we take into account the evapotranspiration, leakages, and seepages as well, and then the area of the sector. So what we're interested here is, what we're saying is, at any point in time, the standing height of water on the field affects the productivity at any point in time. So if we can find out the standing height of water, then we can, if we have the discharge, the discharge, then we can compute the standing height of water. This is of course not a differential equation, and the relationships at the bottom is a set of constraints from the block diagram that from the network diagram that we drew. All this set of constraints we have to be matched. And I mean, to get water to one of the sectors, this is the combination of gates that we have to be open. Again, I mean, there's the same model over there, and then it's a network. There are nodes, so water is coming in, water is going out, and then the mass balance, which is represented by the earlier equations, has to be, those are the constraints. So the differential equation that we solve with respect to the given constraints. Now, one more thing is required before we run our simulations, that is to come up with a measure of performance. The way we have conceptualized performance is we say that, well, we understand that there are many factors that will affect the yield or the productivity of the system. But one of the critical factors we say is water. And now we're keeping all the other factors constant, and we're only taking a look at water. And based on that, what we do is we look at 2 conditions. If water cannot be supplied at the right volume at the right time, then it falls under the band that we created earlier. So that would be a situation of drought. If there's more water coming into the system, then that would be a situation of flood. And then based on that, we compute D, that it is a coefficient for flood as well as drought. And then the coefficient multiplied by performance. The idea of performance is 100%. If you can supply water at the right time and the right place, right volume, D would be 1. Otherwise, it comes from 1 to 0. And during the droughts, there are 4 stages that we recognize, and the most important is number 1, which is the field preparation, and therefore it has a steep curve. If water is not supplied at the right time, then the D factor comes low, and that affects the productivity. Now, based on this, once we've constructed this, then we do our analysis, and this is based on, we look at the variation in river discharge, and the three factors, shifts in the seasonal nature of the river flows. And these are looked at based upon the routes that can be based on the routes that can be used to distribute water, which is open flow, sequential flow, 12 hour, and 24 hour. Now, if at the nominal condition, the river discharge would be at 100%, but there can be a variation in the discharges. It can come from 100 to 30%. So in the lower graph, we see that when the river discharge is at 100%, it is well within those bands. It's only at 50% that it comes outside those bands. And this is for sector 1. Now, this is the water supply profiles when the rules followed are the sequential system, when you supply water to the first and second and the next. This is the type of profiles that we get. Now, this is again a profile on if water is distributed on a 12-hour and a 24-hour basis. Now, combining all of these three different sets, the 12-hour, 24-hour, and the open flow and the sequential, we draw a yield profile over here, and we see that the green, for when discharge comes from 100% to about 50%, the policy that trumps is your open flow. So the best policy to have is have an open flow. And it changes when it comes from 50% downwards, then the best policy changes from an open flow to a sequential flow. Now, sequential flow, this is an optimized sequential flow, and this would be the sequential flow. Basically, when you talk about an optimized sequential flow, what it means is we're working at the lower limits of the band. That would be a optimized sequential flow. Now, if the monsoon comes later, if time shifts, then what would the profile look like? Well, the yield versus the time shift, we see that for about 25 days, open flow policy is still the best policy, and then it changes to sequential. It's like the previous. Now, this is the impact of canal losses, and when you have lots of canal losses, for instance here 3 liters per second, then the best policy is your 12 hours. If you go 12 hours, that would be the best policy. Whereas if your canal losses are minimum, that would be a free flow. Now this is the impact of diversion structure. If the structure washes out, if the diversion structure washes out, then there are two ways of solving this problem. One, I mean, people get together and within 5 days, they get it back together, and some of the water is flowing. In another case, they take about 8 days before water starts flowing in. And for this situation, what is the best policy? We find that the best policy here is again is a 12-hour policy. And we use the Gini coefficient there. I mean, if you look at it, this is a 12-hour policy. It's the most equitable policy as well in that set of conditions. Now, I don't know, I'll just go there. So, what we find in our paper is under close to nominal conditions, open flow and 12-hour locations are the best strategies. So, that would be the best strategies, and that is what the farmers are doing. And we find that the farmers are doing and what the market is. When discharge decreases down to 40 to 50%, sequential rotation becomes the best policy. And this is exactly what the farmers do during the first stage, during the field preparation and the transplantation stage as well. For time shifts and discharge up to 25 days, open flow is the best policy. But in this case, we do not know what the farmers do because they have faced this situation. So there is close agreement between the model and what farmers practice. And to conclude, what I would like to say is when climate, I mean, there is a certain capacity for small systems to adapt and respond to the shocks to their system. But then, when they move beyond a certain threshold, then institutional arrangements can do only so much. And they cannot be expected to cope with significant climate changes. Example, 6 in monsoon, if it's 3 to 4 weeks. And this can be very difficult. Thank you, I've finished my time. Thank you very much.